Yeah, hello everyone. Good afternoon to all of you. So can you hear me? Am I visible and audible to all? Yes. Okay. Thank you so much. So now, yeah, good afternoon, Pratika. Good afternoon to all. So now, let's continue with the coordination complex. Okay. Yeah. Yes. Thank you. Thank you, sir. Fine. So yesterday we have completed the crystal field theory, right? So we have completed all the theories of this lesson. So we are just about to complete this lesson today. I'm going to start with a new lesson today. So the last two small topics of this lesson are the bonding in metal carbonyls and applications of coordination compounds. Okay, which are basically coming under this CFT. Bonding in metal carbonyls will come under the CFT part. And then we will discuss the applications of all the coordination compounds, and then we will finish this. So moving on to the bonding in metal carbonyls. So let me show you the structures of some important carbonyl complexes. So what is meant by metal carbonyl first of all? What is meant by metal carbonyl? So the complexes which have the carbonyl molecule as a ligand. The complexes which have carbonyl molecule as ligand is called as metal carbonyls. Okay. So there are two different types of metal carbonyls. One is homoleptic complex and the other one is heteroleptic complex. So we all know the definition of these two statements, right? Homoleptic means the same type of ligand will be present inside the coordination entity. And in case of heteroleptic, two different or three different types of ligands may be attached to the central metal atom in the complex. Got it? So metal carbonyls can be of both types. Okay, we may have all same type of all ligand as CO, or in some cases 4 CO and 4 Cl. I mean 2 Cl. So such kind of heteroleptic is also possible. Now I am going to discuss the homoleptic complexes of this metal carbonyls. The first example for you is nickel tetracarbonyl, which is NaCO4, and it is tetrahedral in shape. And the next one is iron pentacarbonyl, which is having trigonal bipyramidal geometry. Okay, this is the trigonal plane, and this is your bipyramidal. If you connect all the three atoms which is there on the plane with the top CO, you will get one pyramid, right? And in the bottom side also, you will get another pyramid. So it is trigonal bipyramidal in geometry. And the third carbonyl is chromium carbonyl, which is having octahedral geometry. CO 6 times now, so it is octahedral. Coordination number 6. So it is octahedral in nature. And some more examples are manganese carbonyl, Mn2CO10. So around each manganese, you can see 1, 2, 3, 4, 5, 6. 6 CO ligands are attached. So each manganese is surrounded by, 5 CO and one more manganese this side. One more manganese. So it is having square pyramidal. So this is the square plane. If I connect this to the top CO, I will get on square pyramid, right? So I'll get a square pyramid kind of structure for this. And the last example for you is cobalt carbonyl. CO2, CO8. This is your metal atom, cobalt, and this is the carbonyl ligand. So 8 ligands are there and 2 metal atoms. Cobalt is present. So all these 5 compounds are the examples of metal carbonyls. Now, what we are going to study? We are going to discuss about the metal, this carbon ligand bond. Metal CO bond discussion is going to happen now. Okay. So for that, let me show you the diagram. So just see this diagram. So there is a metal. And this is our D block metal atom. This is the D block metal atom. And to this metal atom, carbon monoxide, which is called as carbonyl ligand, is attached to the metal atom as a ligand. Now, all the metal atoms are having d orbitals, right? So there are 5 d orbitals. So metal will have 5 d orbitals. 2 orbitals are shown to you. So one is given in the pink color. So you can see this is one orbital. This is one of the d orbital, okay, which is having double dumbbell shape. So that orbital is filled. That orbital is, you can see this particular orbital is having filled electrons. Electrons are located, so it is filled. And one more d orbital is shown to you with one lobe. Actually, it will be like this. Okay, it will be like this. And this orbital, if you see, this metal orbital is empty. Got it? This is about this metal. And coming to this ligand, CO ligand is having two different types of orbital. One is called as bonding orbital and the other one is called as anti-bonding orbital. So this green color with this, it is actually called as, both together are called as bonding molecular orbital. Okay. And the other one, the pink color, these two and these two, they are called as anti-bonding molecular orbital. They are called as anti-bonding molecular orbital. Got it? Now, anti-bonding molecular orbital is empty for this ligand, and bonding molecular orbital, you can see this green color and this pink color. Bonding molecular orbital is filled for this ligand. Got it? Now, what is going to happen? The filled orbital of this ligand is now going to transfer its electron to the empty orbital of metal. Okay. So the transfer of electrons from the filled ligand orbital to the empty metal orbital is now going to form one bond, which is called as sigma bond. Because you can see there, the overlapping is between, it is in the headwise manner, right? It is in the head-on overlap. That overlap is called as, this overlap is called as head-on overlap. So the filled orbital of the ligand is transferring the electron to the empty orbital of metal in the headwise, head-on manner. So it leads to the formation of sigma bond. Okay, now this filled orbital of metal is transferring its electron to the empty antibonding orbital of ligand. They are transferring the ligand, transferring the electrons. So electron is present here, and this is the antibonding orbital of the ligand. Okay, this is the antibonding orbital of the ligand. Here the electrons are transferred. Now you can see the overlapping is in the sideways manner. So this is called as sideways overlap. So the sideways overlap of the system leads to the formation of pi bond. Okay. So in one side, ligand is donating and forming the sigma bond. In the other side, metal is donating and it is forming the pi bond. Okay. So ligand is also donating, metal is also donating. So what happens? So the metal ligand bond possess, so this metal and the ligand is there, no? So this bond possess both sigma and pi character. This bond has both sigma and pi character. Got it? So what is happening because of this? This is called as back bonding. This is called as back bonding. So metal is also donating. In the other side, ligand is also donating, right? So this is called as back bonding. And this sigma and the pi character of this particular bond increases the strength of the bond. This increases the strength of the bond. This increases the strength of the bond. So metal ligand bond is very, very strong. Metal ligand bond is very, very strong. In one case, donation of electron from CO to metal by sigma bond. And this metal ligand bond is very strong. And this effect is called as synergic effect. This effect is called as synergic effect. This possessing the sigma and pi character of that metal ligand bond, no, that effect is called as synergic effect. This effect strengthens the metal carbon bond. Okay, this is called as synergic bonding. This process is called as, or this concept is called as synergic bonding. The synergic effect strengthens the metal ligand bond because it has both sigma character as well as pi character. Got it? So this is the concept you are going to get from this particular topic. Any doubt? Any doubt? Any doubt? If it is clear, just type yes in the chat box. If it is clear, just put yes in the chat box. Shall I move on with the next topic? Shall I move on with the next topic? Yes. Okay, Mukavan. So the next topic is applications of coordination components. Applications of coordination components. The very last topic of this lesson. Okay. So first application is coordination compounds are used for the estimation purpose, estimating the hardness of water. So we do have two different types of water, right? Hard water and soft water. In hard water, we have several types of ions like magnesium ion, calcium ion, bicarbonate ion, chloride ion. So all different types of ions will be there. Now what we have to do, we have to remove those ions from that water. Then only we can use it for drinking purpose, right? Hard water cannot be used for drinking purpose. So we have to remove the ions which is present there in the water. Now for this removal purpose, removal of hard ions, coordination complexes are used. So first, the given magnesium and calcium ion in the hard water is titrated with the sodium EDTA complex, which is the coordination complex. Okay. So when you treat this with this, it forms a stable complexes of calcium 2+ and magnesium 2+. So the calcium ion and magnesium ion present inside the hard water is now going to form the complex with this EDTA, coordination complex with this EDTA. And this sodium will come out. Okay, because calcium magnesium complexes with the EDTA are more stable than sodium EDTA complex. Got it? So I'll show you. So sodium EDTA is a weaker complex, but magnesium calcium EDTA is a complex, stable complex. Got it? So like this, we can, by using this, we can remove the hard ions from the hard water. Got it? So this is the first application. And coming to the second application, it is used in the extraction process of silver and gold. In the extraction process of silver and gold. You might have studied this in your metallurgy lesson, if metallurgy lesson is taught to you in your schools, but it is deleted for now, right? So you might have not studied that. So these reactions are there in this lesson. So silver is there and it is treated with NaCN and oxygen and H2O. So there is a formation of one compound, which is nothing but the coordination complex. Yes, Mohammed, you have raised your hand. Any doubt you have? You have any doubt, Mohammed? No. Okay, no problem. Fine. So here for the extraction of metal and for the extraction of gold, the silver and gold, extraction of silver and gold, coordination complex is formed in one of the step in the extraction process. And this compound, they can be further extracted by dissolving the complex solution with zinc. So these two coordination complexes are treated with zinc. Okay, they are treated with zinc and the pure gold and pure silver will be extracted from this process. So coordination complex is used in one of the step in the extraction process of the metals. Got it? This is the second application. And coming to the third application, it is used in the purification of metal. Like in case of Mons process, impure nickel will be converted to pure nickel. So what they will do, they will get the impure nickel from one step. So that impure nickel consists of some impurities. So it is treated with the carbon monoxide, carbonyl ligand, and it is forming this nickel tetracarbonyl complex, which is nothing but the coordination complex. Okay. Now, this nickel tetracarbonyl complex undergoes decomposition, and once the decomposition occurs, the nickel tetracarbonyl will give nickel and 4CO ligand back again. Now, initially we took one nickel and 4 carbon monoxide was added to that, and which leads to the formation of this complex. Then again, this complex on decomposition leads to nickel and 4CO back again. So what is the difference between this nickel and this nickel? The first nickel is impure, but the second nickel is pure. So in between, coordination complexes form. So it is coordination complexes are used for the purification of a metal like nickel. Got it? This is a third uses of applications of coordination compounds. Coming to the fourth application, it is also having some biological importance. Like in case of chlorophyll, we have the magnesium complex, magnesium containing coordination complex. And in hemoglobin, iron complex is used. And in case of vitamin B12, cobalt complex is used. So all the three are coordination complexes only, where we have metal ion at the center and ligand surrounding them. Okay, these are all the biological importance of these compounds. And coming to the fourth property, fourth application, it is also having some application in enzymes. In carboxypeptidase A enzyme, we have this coordination compound, and zinc will be present as metal, central metal atom there. And in case of carbonic anhydrase enzyme, okay, we have zinc again. So both enzymes are zinc complexes. They are present in the enzymes also. Metal ion with ligands together as a coordination compound is present in the enzymes. And in case of industry, it's also having some industrial importance. Like Wilkinson catalyst, this rhodium containing rhodium triphenyl phosphine and chloro ligand containing complexes are coordination complex, and it is called as Wilkinson catalyst. So this catalyst we are using in organic chemistry for the hydrogenation of alkene. What is hydrogenation of alkene? Addition of hydrogen to alkenes, double bond. Addition of hydrogen to double bond. So this is your ethene. This is CH2 double bond CH2, and to this compound we are breaking this bond and adding hydrogen. So C2H6 is formed. So here Wilkinson catalyst is used as a catalyst. Got it? Fine. And coming to the next property, why all of a sudden most of the people have left the meeting? Any issues? Any issues? Do any of you have? All of a sudden, many people have left the meeting. They belong to the same school or what? I know. Okay. Fine. So the next use is the electroplating with silver and gold. In the electroplating process, if you see, so the gold cyano complex and silver cyano complexes are used. So electroplating is nothing but the coating which is made in all the metals. Okay, but to prevent the rusting, they use this electroplating technique. Okay, in all the cars and all, you can see there will be a plate, right? All the car metals. In bike also we have the metals which is covering all the parts. So they are electroplated. So they are electroplated to avoid the rusting purpose. So in that electroplating solution, this gold containing complex and silver containing cyano complexes are used, which are the coordination complexes. Okay, so it is done with complex solution, which makes the coating even. And also they are used in the polarography, black and white polarography. Coordination complexes are used. The uncomposed AgBr on the film is used, and it is washed with the hyposolution, and that hyposolution is nothing but this AgS2O3 twice 3- solution, which is the coordination complex. And this complex can easily be washed away. So since it is a coordination complex, it can be easily washed away, and that's why they are using this coordination compounds in the solution. Okay, so this is one of the application. And coming to the last application of coordination compound, they are also used in chelate therapy for all the cancer causing treatments. In all the cancer treatments, they are using this coordination complex in the chelate therapy. So the excess of copper is removed by D-penicillamine compound by formation of the coordination complex. And the excess of iron in your body is removed by desferridoxine B chemical by the formation of the same coordination complex. And in case of lead poisoning, in case if you're affected with lead poisoning, then it is removed by lead poisoning is removed by EDTA by forming the lead EDTA coordination complex. Okay, and the cisplatin, it inhibits the growth of tumors. So this is what I have told. This is the cisplatin. This compound is used majorly in for treating the cancers. Okay, so it stops the growth of all the tumors inside the body. So it is used. So where it is a coordination complex. Got it? So it is used in the chelate therapy purpose. So with this, the lesson gets over for us. Do any of you have any doubts in this lesson? Oneness theory and nomenclature, isomerism, valence bond theory, crystal field theory, color of the complex, bonding in metal carbonyls, and applications. So we will solve some more questions related to this lesson in this weekend's class. Okay. So in last Sunday we have discussed coordination compounds questions. Last Sunday we have discussed, and coming Saturday also I'll discuss some of the questions from this coordination compounds in coming Saturday's weekend's class, and some of the questions from P block. Okay. So if you're having any doubt here in this lesson, you can ask me. I will give you 1 or 2 minutes. Now, within 1 or 2 minutes, we will start with the next lesson. By the way, if you're having any doubt, you can ask me. Okay. You can think for your doubt and you can ask me. No doubt? Everything is clear to all of you? Okay. No doubt. No doubt for Sandeep. Okay. That's great. So go through the lesson once again and try to solve more number of questions. So as I have told you, we will solve some more questions on this lesson on coming Saturday. Try to join the class on Saturday. So now I'll, yeah. Now I'll start with a new lesson, which is called as the P block elements. Which is called as P block elements. So coming to this lesson, already this lesson is deleted for you in your board. Okay, so you might have not come across this particular lesson in your school. So in the periodic table, we have 4 blocks, right? S block, P block, D block, and F block. The P block elements consist of group 13 till group 18 in the periodic table. Okay. Group 13 and group 14 elements are there in the 11th class, and from group 15 till 18. So these 4 groups are discussed in your class 12. Okay. So now, since we all belong to class 12, I'm going to deal with group number 15 till 18 for you. Okay. So coming to the lesson, it is one of the very important inorganic lesson for you. And some of the portions are deleted in this lesson. If you are referring the old version of NCERT, some of the lessons are deleted in that. Some of the parts are deleted from that. So you just see to note, make a note of it and study accordingly. Don't study all the deleted parts and all. Okay. Fine. So coming to the P block elements, as I told you, the group 13 till 18 elements are P block. So what is the general electronic configuration for P block? It is NS2 NP126. NS2 NP126 except this helium. Helium is not having NS2 NP126. It is having only NS2. That is 1s2. That is a configuration. No p orbital for helium. Okay. But it is located in the P block because it is one of the inert gas. That's why it is located in this block. But it is not a P block. I mean, it is not having p orbital. Okay. Exception is helium. And in this particular picture, you can see the color differentiation given for some elements. So there is a blue color element. There are some blue color elements which are aluminium, gallium, indium, tin, thallium, lead, bismuth, and polonium. So these are metals. All the blue color elements shown to you are metals. Okay. And the green color, some light green color is shown to you, right? That they are metalloids. Metalloids are nothing but the semi-metals. Metalloids are semi-metals. And the red color part, they are non-metal. Red or orange, some light orange kind of metals are, they are non-metals. Those elements are non-metals. So there is a diagonal: boron, silicon, arsenic. Actually, this is not arsenic, this is germanium. Yeah, germanium, arsenic. This is antimony, selenium, tellurium, and astatine. So these elements are metalloids, and the diagonal which is present above, the diagonal which is present above the semi-metals are non-metals, and the lowest diagonal, they are metals. Okay. And the 17th group elements are called as halogens. 18th group elements are called as noble gases or inert gases. These are the very special name given to these two group elements. Got it? So I'll go in detail with this. The P block elements uses. So where we are using this P block elements? For example, silicon is used in computer chips. You know, on the computer, that circuit chips, you can see silicon is being used there, which is a P block element, and silicon is a group 14 element. Okay. And borax. Borax is a compound which contains boron. Boron belongs to 13th group. So in optical glasses, borax is being used, and boron is also found in the cell walls. It is also found in the cell walls of plants. And carbon, we all know, it is a 14th group element. It is found as graphite in pencils, and in the diamond also we are having carbon, right? In diamond also we are having carbon. So these are the P block elements which are being used in the daily life. Now we are going to deal with group 15 till 18. So the first topic for group 15 is the general concepts about group 15 elements. So under this particular topic, we are going to discuss basic concepts of group 15, physical properties, chemical properties, and anomalous behavior of nitrogen. Okay, anomalous means different behavior, some kind of unique behavior of nitrogen. So these are the 4 topics we are going to discuss, and all the 4 topics are included and they are very important for you. Okay, not even a single topic here is deleted. So you are going to study these 4 topics from group 15. So likewise, the same 4 topics: basic concept, physical, chemical properties, and anomalous behavior of oxygen. They will be discussed in group 16. Okay, in group 17, in group 18. So this is the pattern that we are going to follow for this lesson. And some important compounds of group 15, important compounds of group 16, group 17, group 18. So those important compounds, you can find it in the older version of NCERT. That part is deleted. Got it? All the important compounds of that corresponding group elements, they are deleted. But all the general characteristics we are having. General characteristics means this physical property, chemical property, general characteristic we are having. Specifically, we are not going to study any compounds of this particular group elements. Okay. So now I'll start with the first topic of this group, which is the basic concepts of group 15 element. So let me show you a tabular column which consists of this group 15 element. So who are the group 15 element? Nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. So these elements are coming under group 15. Okay. And symbol of each element is given to you, atomic number, atomic mass, and the nature is the physical nature, that is characteristics, is given to you. So if you see nitrogen, nitrogen is having atomic number 7 with the 14 atomic mass. It is a non-metal. For nitrogen, you have to study the atomic number and atomic mass. Okay, it is very important. And coming to phosphorus, atomic number is 15. Atomic mass is 30.97. In most of the problems in your class 11, we use the atomic mass for phosphorus is 31, right? That you have to keep in mind. And for arsenic, arsenic is a metalloid. Antimony, you have to see the symbol of all the elements. They are very important. Antimony is having SB symbol. Okay, it is a metalloid. And bismuth is also, bismuth is a metal. And moscovium is also a metal. So first two is non-metal, the second two is metalloid, and the third two is metal. Got it? Moscovium is also a metal. The general electronic configuration for group 15 elements are NS2, NP3. So in NS orbital, we have 2 electrons, and in NP orbital, we have 3 electrons. If I have to write the electronic configuration of nitrogen, what will be the value of N for nitrogen? What will be the value of this N for nitrogen? Can anyone tell me the value of N for nitrogen? Nitrogen belongs to which period? Nitrogen belongs to second period, right? So the N value will be 2. So the configuration will be 2s2 2p3 for nitrogen. And phosphorus belongs to third period. Arsenic is fourth period, fifth period, sixth period, and seventh period. So you will have 2s2 2p3 for nitrogen, 3s2 3p3 for phosphorus, 4s2 4p3 for arsenic, and it goes on. Okay. And this particular group, they have the extra stability. Can you tell me the reason for the extra stability attained by this group elements? What is the reason for the extra stability of these groups? Any idea? It is because of the half-filled configuration. Half-filled, yeah, very good. Half-filled electronic configuration of p orbital. Okay, half-filled configurations are more stable, right? So that's why group 15 elements are relatively more stable compared to the other groups. Okay, so this is about the basic, very basic concept of group 15 elements. And next, we will move on with the occurrence of group 15. So the nitrogen, let me start with the nitrogen. So nitrogen is there existing in the atmosphere, where 78% by volume is occupied by nitrogen gas. This one we are studying from our childhood days, right? 78% by volume is occupied by nitrogen. And it is also present in 2 salts. One is child saltpeter of formula NaNO3, the other one is Indian saltpeter. In these 2 salts, sodium nitrate and potassium nitrate salts, nitrogen is existing. And it is also one of the constituent in plants and animals. Okay. In plants and animals, we have compounds like, in proteins, we have amino acids, right? Amino acids are forming the proteins. And in this protein, which is formed by amino acids, you can see nitrogen will be one of the atom in that amino acid. Okay. So that's why it is a constituent in plants. And in case of DNA, in DNA, the double-stranded DNA, it is formed by the nitrogenous bases, right? That adenine, guanine, cytosine, and thymine. So they are nitrogenous bases, which consist of nitrogen. So in that also, in DNA also, we have nitrogen. Got it? So nitrogen is existing in atmosphere by 78% by volume, and in shell saltpeter, Indian saltpeter salts, and it is present in the constituent in plants and animals. Got it? Now coming to the second element, which is phosphorus. Phosphorus is existing in its ore form. The ore of phosphorus is apatite. So calcium phosphate, calcium halide ore it is. So in this ore, you can see phosphorus as one of the component. Okay. And it is also present in ATP and ADP. Adenosine triphosphate and adenosine diphosphate. You can see this phosphorus, and phosphorus is also present in bones. It is also present in our bones. Okay. And it is also there in egg yolk. It is also there in egg phosphorus. Some small amount of phosphorus is present in the egg yolk. Okay. So these are some of the occurrence of phosphorus. Then coming to the remaining elements, arsenic, antimony, and bismuth, they are present in the sulfide minerals. They are the sulfide minerals. Arsenic sulfide, antimony sulfide ores contain arsenic and antimony as the element. And in case of bismuth, it is also present in its bismuth sulfide ore only. Okay, bismuth sulfide ore, bismuth is present. And the last element of this group is moscovium, right? Moscovium is a synthetic radioactive element. What is meant by radioactive? Man-made element. Radioactive elements are man-made elements. So it can be synthesized in the laboratory or some special atmosphere. It is not existing in the atmosphere. It does not have natural occurrence. We can synthesize that element. It is having very, very short half-life. So only very little amount of it can be prepared in the laboratory. Okay. So these are the existence of group 15 or the occurrence of group 15 elements. So any doubt from the occurrence part? Any doubt? Any doubt from the occurrence part? Just you have to study the compounds from which it is getting. Okay, the occurrence. The name of the mineral, the name of the ore, and in which part it is present. Those things. Yeah, no doubt. Okay, then I'll proceed with the next topic, which is the physical properties of group 15 elements. So the first property to discuss about the group 15 is the electronic configuration. This I have already explained with you. So nitrogen will have NS2 NP3 outer electronic configuration, but the complete electronic configuration is given to you. So where helium will be the nearest noble gas for nitrogen. With helium configuration, you have to add NS2 NP3, and the next noble gas is neon. With neon, 3s2 3p3 for phosphorus. And coming to arsenic, d orbitals are involved, and for antimony also d orbitals are involved, and for bismuth also d orbitals are involved with xenon. Okay. So for the first two elements, for nitrogen and phosphorus, d orbitals are not present. Okay, but for arsenic, antimony, and bismuth, we have filled d orbitals. We have filled d orbitals. You should take a note of it. Very important. So this is about the electronic configuration. Then coming to the trends in physical properties, the first physical property is atomic and ionic radius. And we will see the atomic and ionic radius and its trend in the group. Okay. So these are the elements, and its atomic radius is given to you. Electronic configuration is also given to you. On moving down the group, you can see the number of the shell increases, right? The shell number increases. Number of the shells increases. And because of this, atomic size also increases. Atomic size also increases. So you can see the size value. On moving from nitrogen to phosphorus, the size difference is very large. 70 picometer. From 70 picometer, it is going to 1110 picometer. There is a drastic change. Okay, from nitrogen to phosphorus. There is a considerable increase in atomic radii. Okay, due to the effective shielding of S and P electrons. But when you are moving from phosphorus to arsenic, the difference is very less. That is some around 10 picometer differences only are observed. And moving from arsenic to antimony also some 20, and here only 8 picometer difference. But from 70 to 110, there are 40 picometer difference, right? So here 40 picometer difference is there. So the large difference is due to the effective shielding of S and P electron. So this is the nucleus. This is shell number 1. This is your shell number 2. So shell number 3, shell number 4, etc. Right? So if taking phosphorus as the case, so for phosphorus, the outermost shell is 3. And in 3s orbital, I have 2 electrons, and in 3p orbital, I have 3 electrons. Okay. So, and also I have 2s2 electrons and 2p6 electrons in the inner shells. So these electrons, which is located in the first shell and the second shell of phosphorus, those electrons will shield. Those electrons will shield more effectively. Okay. So the outermost electron, which is there in the third shell, cannot get attracted towards the nucleus. So the attraction is very less. If the attraction is very less, then the contraction in the size is not observed properly, right? So the size remains as such. Size remains as such. So what happens? There is a considerable increase in the size. There is not decrease. But when you are moving from phosphorus to arsenic, there is only a very small increase due to the ineffective shielding of D and F electron. So if I am going for, what can I say? Okay, I'll take arsenic. Okay, this is the nucleus of arsenic. Shell number 1, shell number 2, shell number 3, shell number 4, and shell number 5. What is the configuration for arsenic? 4s2, 4p3. So in the fourth shell, electrons are present, and we have D electrons in the third shell. We have D electrons in the third shell for arsenic. No F electrons for arsenic. Okay. For bismuth, you will have F electron, but for arsenic, you will not have F electron, only D electron. So the electrons, the D electrons which is present there in the third shell, they will not shield the outer electron properly. Means there will be some space. So what happens? The outer electron which is present there on the fourth shell can get attracted towards the nucleus more effectively. They will come towards the nucleus. Since the shielding is very poor, they can come and get attracted. So contraction occurs. So the size becomes very less. Okay, that's why there is a very small increase in the size because of the very small size of the next atom from phosphorus to arsenic. Okay, clear? So when you're going from antimony to bismuth, you can see F electrons are also there inside that. So both the D and the F electron, they will not shield properly, which leads to the contraction in size. So there is not very big difference observed for arsenic, antimony, and bismuth. Got it? Any doubt? Is the concept clear to all of you? If you are having any doubt, put it in the chat box. If the concept is clear to you, then type it is clear or type yes or something. I will go on with the next topic. Shall I move on with the next physical property? The trend is on moving down the group, atomic size increases. Okay, that is the trend. Okay, fine. Next, I'll go with the ionization enthalpy. Second property, second physical property is ionization enthalpy. What is ionization enthalpy? You might have studied this in your class 11, right? What is ionization energy? Can anyone tell me the definition for ionization energy? The energy required to remove the outermost electron from an isolated gaseous atom is called as, yeah, very good, Sandeep. Energy required to remove the outermost electron from an isolated gaseous atom is called as ionization enthalpy. So, and gaseous atom, isolated gaseous atom, it will absorb some energy. Okay, the energy which we are giving, it will absorb, and outermost electron is removed from that. Now, the nitrogen, phosphorus, these are those elements, isolated elements. Energy required to remove the outermost electron from nitrogen, you see, it is 1,402 kilojoule per mole, whereas in case of phosphorus, it is very less. And it is decreasing. So, atomic size and ionization energy, they are inversely proportional to each other. So, this concept you might have studied in your last year itself. Atomic size is inversely proportional to ionization energy. Since the size increases on moving down the group, ionization energy decreases. Okay, so why it has to decrease on increasing the size? The nucleus attraction towards the valence electron decreases when you move down the group. So this is your nitrogen, phosphorus, arsenic, antimony, and bismuth. So what happens? The distance between the nucleus and the outermost electron increases on moving down the group. If distance increases, attraction decreases, right? So that's what is given here. The nucleus attraction towards the valence electron is decreasing. So because of this, we can easily, this is called as shielding effect. So we can easily remove this outermost electron. So that's why the ionization energy decreases on moving down the group. Okay. And also you have to make a note of it. We can remove we cannot remove only one electron. We can remove 2 electron, 3 electron also. If the energy required to remove the first electron is taken as delta H1, then energy required to remove the second electron is delta H2. Then the energy required to remove the third inner electron is called as delta H3. Okay. But among these three, the third ionization energy will be very high. Because you are going inside, no? Well, on removing the electrons, we are going inside. If we are going inside, the attraction will be very high. So more amount of energy is required to remove the last electron, which you are removing. So the energy required to remove the third electron is very high compared to second, compared to first. Okay. And this particular ionization energy for group 15 elements are relatively very high. They are very high. You can see they are very greater than group 14 and group 16. Why? Because of the extra stability of the half-filled configuration. Okay. So group 15 elements are having half-filled configurations, right? So they are very, very stable. So to disturb a stable person, you have to supply more amount of energy. Then only you can remove this electron from the system. Okay. So you have to make a note of it. So this is about the ionization energy. And the trend observed for ionization energy is decreasing on moving down the group. Okay. Clear for all? Shall I move on with the next physical property? Yes or no? Say yes or no. Okay, I'll move on with electronegativity. Yes. Third physical property is electronegativity. What is electronegativity? Ability of an atom to attract the shared pair of electrons towards itself is called as electronegativity. Right? Ability of an atom to attract the shared pair of electrons in a bond of molecule is called as electronegativity. So you just see here, 2 atoms. One is violet colored atom, the other one is blue colored atom. But what this blue color atom is doing? In a bond, we have 2 electrons. But blue color atom is pulling the violet color atom's electron towards itself. So atom A is having very weak pull, but atom B is having very strong pull. So atom B is more electronegative now, right? So the electronegativity is measured using the Pauling scale, and some values are given to each element in the periodic table for electronegativity. And for group 15 elements, electronegativity values are shown to you on the screen. For nitrogen, it is 3. For phosphorus, it is 2.1. For arsenic, it is 2. For antimony and bismuth, it is 1.9. So what happens? Electronegativity decreases on moving down the group. So atomic size is again inversely proportional to electronegativity also. Okay. As atomic radius increases, the effective nuclear charge decreases. So the electronegativity decreases. Okay. So, and the electronegativity is very greater than group 14 elements due to the greater effective nuclear charge of group 15. Okay. So don't worry about the effective nuclear charge. It is a charge which is present inside the nucleus. Okay. So that concept and all you might have studied in your class 11. Okay. So this particular relation, you just make a note of it. And nitrogen is the third most electronegative element in the whole periodic table. First most electronegative element is fluorine. Second most electronegative element is oxygen. Third most electronegative is nitrogen and chlorine. Okay, so here nitrogen is coming in the third place in the periodic table for electronegativity. Okay, so this is the trend. Then, what is the time now? It is 4:54. So I think this is enough for today. So what we have discussed today, we have discussed the occurrence of group 15, and secondly, I have discussed the physical properties of group 15. And in physical property, the first is general property about the electronic configuration, and the second property is about the atomic and ionic size, and the third property is with ionization energy. Fourth property is electronegativity. Okay, the next physical property and the remaining part and chemical properties we will discuss in the next class. Clear? So go and study this lesson. So in the coming weekend's class, we can solve questions also from this lesson. So before that, you also try to solve some questions before coming for that class. Okay. So if you're having any doubt, you can put it in the chat box now. If you're not having any doubt, you can leave the class. Thank you so much for listening to today's lecture. Thank you. What about Moscovium electronic configuration and size? Yeah, that is a good question. Moscovium is radioactive, right? Moscovium is radioactive. Radioactive means it is a man-made element. They will not be stable. We can able to study the physical properties, chemical properties only for the element which is stable. Since Moscovium is unstable in nature, its half-life also I have told you, it is very, very short. It will exist for very few seconds and then it will go off. The element is not stable. You cannot keep the element in the lab or you cannot keep the element in some place and you can study. Okay, it will go off, it get decomposed or something will happen and it will be, what to say, it is unstable. It is not existing in the atmosphere. So we cannot study the properties of the element which is unstable. Got it? That's why all the physical properties and chemical properties are not studied for Moscovium. So in all the groups, it will be the case. In all the groups, the last element is radioactive. So those elements' properties will not be studied. Only the first 5 elements, physical and chemical properties will be discussed. Okay? Clear? Fine. Okay, dear. Thank you. Thank you so much for all. Bye-bye. Yeah. Bye-bye.